Did anyone get a chance to look at the reading for? Did you guys like the decision tree with the D3? No. So this one was in the meetup. So I just shared sort of a animated read through. Okay, yeah. So well, the homework was quite intense, I think, for last week, but yeah, it's very important to get those skills. But the idea is that you can come back to those data frames as you need to go start probing the data more and more. So the entire programming guide is actually Databricksified for you in Scala, which is, so it's not just me doing it, it's quite a lot of people helping. So it's really good. Of course, we cannot just Databricksify the machine learning programming guide. That's actually a serious project. So I'll just try to give you just like sort of expositions and expansions on existing notebooks that are already in the Databricks guide or in the community edition of Databricks. Okay, so let's sort of get started. You may want to clone week 4, which is here. And we will just get into machine learning introduction now. Okay, so here are the resources I'm kind of trying to weave around. So I'm not an expert in every single algorithm in machine learning, of course. So I'm sort of reading these things as I go with you, basically. Right. So the main, there's sort of the Stanford gang of 3: Hastie, Tibshirani, and Friedman. So this book called Elements of Statistical Learning is what I had as a recommended reading when I was a grad student. I really like this book, and I highly recommend it. There is a more recent January 2014 Stanford University professors, again, Hastie and Tibshirani. They wrote this other book, which is more focused on R. It's called An Introduction to Statistical Learning with Applications in R. This book is freely available right here. And this is actually 15 hours of expert videos in machine learning. So you don't need to go to like Stanford or New York City if you have 15 intense hours, so not continuously, but breaks. So you can essentially get into here. So here are all the slides and playlists and so on. I'm not going to, I'm just going to provide links to some of these videos to give an alternative perspective to the perspective we will predominantly follow, which is again, the Scalable Machine Learning course of Amit Talwalkar. So this is just there for sort of an extra perspective for now. Okay, so a more theoretically sound book with very interesting applications is this one. As I said, there's actually a solutions manual for it as well. Again, this is a better course, as I think the data mining course in the stats department used to use this book. So our main thing we'll be weaving around is the 2015 University of California, Los Angeles. This is Amit Talwalkar's course. And Amit is actually from the Spark team. And this is the Berkeley XCS 190.1x course. This is the second part in the last year's series on big data that myself, Steve, completed. And this is a very, very nice course. It goes quite fast and it's quite good. So of course, I told you already that the 2016, this year's version of the same edX course is into a 5-module series, and it's woven on top of Databricks just like we're doing it. And apparently it's in 3 languages. It's going to be released quite soon. Could everyone on the streaming end please mute your microphones, because I can't control your microphones. Thanks. So that course is actually available, and you can do that as well if you want. All right. So of course, those at, well, we have UC Berkeley, UCLA, and this is UC Ilam. So those at UC Ilam, they want to take the following honors courses. So I'm actually sitting on Kurosh Nishantian, who's a machine learning expert in computer science department downstairs. So his course is from 9 to 11 on Fridays. I'm kind of sitting in on it. In fact, this week's material is actually completely complementing what Kurosh is covering right now in machine learning course, right, which is on decision trees. Okay, of course, we also have a data mining course from our school here, Maths and Stats, and I think that's in semester 2, is that right? The data mining course?
Semester 2.
Yeah. So that's for more of applied statistical learning methods, and I believe they're using this book for that. So again, that's another way to get more depth on data mining or statistical learning. My own preferred book for statistical learning since 2 years ago is the one by Kevin Murphy. Okay, so this is basically what I kind of carry around now. So this is a very beautiful book. It's machine learning from a probabilistic perspective. The notation is quite tight and consistent for the entire book, which helps a lot. And there are minor typos, but they're sort of very grammatical and sort of obvious typos. So it's quite a good book. So it's what I'm basically falling back on. And it gives you all the code in MATLAB, which should be almost octave compatible. And every single image basically has an M file, a MATLAB file that you can go and download. And so it's algorithmically tight, code-wise tight, mathematically fairly tight. And there are pointers to go into more theory if you like. Okay. Now, of course, there's a huge mixed audience here. There are sort of professors here who know a lot more about a lot of things than I do. And there are also people from industry who have very, very concrete applied goals. So this particular course is actually an applied course in data science. Okay, it's called Scalable Data Science because unlike sort of traditional data science over the last several years, in the last 5 years or so, or 3 years or so, Scalable Data Science is essentially distributable and, sort of you think about things from these commodity hardware point of view, and then Spark sort of took this Hadoop perspective and made it in memory, right? That's why it's called Scalable Data Science. But this is a very applied course. What I mean by that is you have to work on your own to get a deeper mathematical understanding. Okay, I'll provide pointers. I'm going to focus on intuition here, okay? And that's sort of the plan. And we're going to mostly, because we're supported heavily by industry, we're going to mainly focus on distributed machine learning pipelines in action, right? So although the examples we'll cover will be small, they should be completely scalable. We should be able to plug in very large data sets and everything should just work, basically. Okay, so now I am actually quite interested in theoretical learning because there are some people here who have the right mathematical background. So I may consider teaching a theoretical course in statistical learning if there is enough interest for those with background in honors level, at least real analysis, some Euclidean geometry, and some honors level combinatorics, and also honors level probability. So people with this sort of background can actually really enjoy a theoretical course. So a particular school of theory that I've been fascinated by for a while is sort of called the L1 School of Statistics. And the main proponent of the school is Luc Devroy. He actually visited our school recently. So we're working on some problems between computer science and here that were motivated by Luc. And also I've done some theoretical work on this sort of L1 school stuff. And here is actually a course I've offered in École Polytechnique where the PhD students have the right background for it. So this is a very, very condensed course, but I'm more than happy to do a more elaborate version of that if people are interested in the future. Okay. Let's now watch some videos, right? This is Machine Learning Introduction, and it's very, very high level by Amit Talwarkar. So let me make sure the volume is fairly high. So Amit is an assistant professor in computer science in UCLA, I think since last year maybe.
In this segment, we'll talk about what machine learning is at a high level, providing a definition, describing common examples of machine learning, introducing terminology we'll be using throughout the course, and defining the two learning settings that we'll be studying. So let's start with the definition of machine learning. It's a wide-ranging field and can be roughly defined as constructing and studying methods that learn from and make predictions on data. This broad area involves tools and ideas in various domains, including computer science, probability and statistics, optimization, and linear algebra. Common examples of machine learning include face recognition, link prediction, text or document classification, for instance, spam detection, which is a canonical example of machine learning, protein structure prediction, or in other words, trying to predict a protein's 3D structure given its amino acid sequence, and teaching computers to play games, such as backgammon or Jenga. Now let's introduce some common terminology we'll be using throughout this course. And to make this more concrete, we'll use the example of spam detection as a running example. So recall that machine learning involves learning from data, and these data points we'll call observations. And observations are items or entities used for learning or evaluation. And in the context of spam detection, emails are observations. Features are attributes used to represent an observation. Features are typically numeric, and in the context of spam detection, they can be, for instance, the length, the date, or the presence or absence of keywords in emails. Labels are values or categories assigned to observations. And again, in the context of spam detection, these can be an email being defined as spam or not spam. Training and test data sets are the observations that we use to train and evaluate a learning algorithm. Again, for instance, in the context of spam detection, this can be a set of emails along with their labels. A training data set is what we give to a learning algorithm in order to train it. And in contrast, a test data set is something that we withhold at training time and subsequently use to evaluate the algorithm or the learning model that we devised. Now let's consider the two common learning settings that we'll be focused on during this course. The first setting, called supervised learning, involves learning from labeled observations. The idea here is that the labels teach the algorithm to learn a mapping from observations to labels. In contrast, in unsupervised learning, we're forced to learn solely from unlabeled observations. And here, a learning algorithm must find latent structure in the features alone. And there's two main reasons why we might want to perform unsupervised learning. One is that it can be a goal in and of itself to better understand our data, to discover hidden patterns or to perform exploratory data analysis. Alternatively, it can be a means to an end. It can be, in some sense, a pre-processing step before we perform the downstream supervised learning test. So what are some common examples of both supervised and unsupervised learning? Well, in the supervised setting, classification is one common task, and the goal here is to assign a category to each item. For instance, spam detection is a common binary classification problem. Here, the categories or the labels that we're trying to predict are discrete, and there's generally no notion of closeness in the multi-class classification set. In contrast, regression is another supervised learning setting where we aim to predict a real value for each item, for instance, trying to predict stock prices. Here, our labels are continuous, and we can, in fact, define closeness when comparing predictions with labels. Now, considering unsupervised learning, clustering is one common unsupervised learning task. The goal here is to partition observations into homogeneous regions, for instance, to try to identify communities within large groups in a social network. The second common unsupervised learning task is dimensionality reduction. Here, the goal is to transform an initial feature representation into a more concise one. For instance, trying to find a more concise representation of high-dimensional digital images represented initially as pixels.
Okay, so we will actually visit some examples of each of those main branches of machine learning. So here's a summary, essentially, in case there's no YouTube. But so the pop quiz now is, what is the difference between supervised and unsupervised learning? Yeah.
So for the first one, you need to supply the training data and you need to actually map from the original data to the results you want to have.
Yeah.
You think they arrive with this one data.
Yeah.
So then unsupervised learning, you let the machine figure out that.
Exactly. There are no labels in the unsupervised setting. Okay, so the quintessential example is there's an expert, maybe a doctor. He looks at the, or she looks at the I don't know, the shape of brain or something from some MRI. And then they decide, well, so this is a diseased brain and this is not a diseased brain based on their expertise. And then those are the labels. So that gives you the sort of training set that you feed into the machine. The machine learns from that training set. And then the task is now, there comes a new patient, there's no doctor around, and you get the scan of the brain. And then the goal is, what can the machine say? Is this person healthy or not, right? So that's essentially a classification problem, a supervised classification problem. Again, it's classification because the labels are discrete, right? Healthy or not, or spam or not spam, or it could be cloudy, rainy, or windy, or whatever. As long as there are discretely many categories, that's classification. And on the other hand, we will see an example later on. We may be interested in predicting the house price based on various features. So there, it's a dollar figure, which is a continuous value. So that's called regression. Once again, regression is typically supervised because you will already have house prices with features, and then maybe you're interested in buying a house and you want to take the features and use some historical data to see if it's really worth the money. Okay.
So could you just talk a bit more about features? So what is the feature?
So features are just projections of the raw data, right? So features can be, usually they're projected to discrete or continuous space, right? So discrete space would be sort of just text strings, things like this, where there's no natural metric or natural distance between these objects. And it could be, in the other case, it'll be just some continuous values like the height of the person, length of the email, or whatever. So those will be real value or continuous value. So those are your features. Feature engineering is this whole process of actually going to the source of the data and seeing how the algorithm performs and doing some model selection, which we will do a little bit of today, and then going back and re-engineering the features, right? The projection from the raw data back to the features. So that's an art, and that's basically where a lot of the insights can be.
Basically, kind of like extracting useful information out of.
Yeah, absolutely. Yeah, exactly. Yeah. So it's just, so the language is kind of now standardized between computer science and statistics. Thank goodness for Carnegie Mellon. And so like the book called All of Statistics by Wasserman, because the two communities diverge. So if you watch the first video from Tipshirani, they talk about how history began in Bell Lab. So anyway. All right, so this is their video. I suggest you watch this later. It's 12 minutes and 12 seconds. These are the guys, the two of the three in the Stanford gang. Quite good. And here is a typical supervised learning pipeline. Okay, so we'll watch this as well, because we're going to do a typical supervised learning pipeline here.
In this segment, we'll review the steps of a typical supervised machine learning pipeline. Recall that machine learning involves learning from data. So of course, the first step of this pipeline involves obtaining our raw data. And this data can come from a variety of sources, including web information, emails, genomic data or other scientific information, images, social data or other graph structures, as well as user ratings or other user feedback. Once we've obtained this raw data, we need to extract features from it. This raw data is typically in an arbitrary input format, and feature extraction crucially allows us to incorporate domain knowledge when representing each of these observations. Additionally, we typically want to represent each of our observations via numeric features. And it's important to note here that the success of a supervised learning pipeline crucially depends on the choice of features.
So does everyone understand what he means by incorporate domain knowledge? So this is a huge misnomer, right? So this is just classically what people have been doing. So if you're extracting information from raw astronomical data, the domain experts are astrophysicists, okay? So the domain experts are completely part and parcel of the data science model. Right? So digital humanities, for example, is a domain expertise. So for example, our little thing we were doing with the State of the Union addresses, right, in the first week, or do word counts. Those are actually, so to really understand it, you need to work with historians, digital humanists that are from the history tradition, right? There are people who specialize on State of the Union addresses. So you need to work with them, otherwise you cannot do really decent feature extraction, right? And that's very, very important. You cannot say digital humanities is the core of data science, right? That's definitely a domain expertise.
Additionally, there's a connection between feature extraction and unsupervised learning. Unsupervised learning can be used as a pre-processing step for a downstream supervised task, and this is typically involved in the process of feature extraction. Once we have a good representation for our observations, we're ready to perform supervised learning, and this typically involves training a classification or regression model on a set of labeled training data. Once we have this model, we want to know how well it's performing. And how can we do this? Well, the natural thing to do is to see how well it performs on data that wasn't used to train. And so we can simulate this process by evaluating it on test or holdout data. And this is labeled data that wasn't used for training. Once we perform this evaluation, we can decide whether we're happy with the current model we have. And if we're not, we can iterate. And this typically involves extracting new features and or trying different supervised learning approaches. Finally, when we're happy with the model that we generated, we can use it to make predictions on future observations, or in other words, observations that really don't have risk.
Okay.
Right.
Yeah.
So the model is basically the algorithm you choose, the features you choose, the interpretation you features, and the labels you apply in training data. Is that the model?
Not quite. So a model, well, there are different kinds of machine learning models, right? So it's one part of the whole package, right? So, so for example, today we'll be seeing decision trees, which is one kind of model.
But this is the algorithm, right?
Yeah, it's an algorithm, that's right.
So the model is the algorithm, or is it also, so he said basically, if you're unhappy with your model, go and change features.
Yeah, and the model itself too, of course. So I mean, yeah, that's right. So you change the features. Say if you're stuck to one particular class of models because your boss's boss says so, then you're stuck with it. Then you can just engineer the features if you're allowed to, right? That's one. But of course, you can also change the model itself. In fact, the most interesting co-evolutions will happen in the operations, joint operations on engineering features and evolving the model, right? So in fact, even today, we will actually see very simple process for this, which is we will fix ourselves to one family of models called decision trees. And even in that family of models, the sort of tuning parameter or hyperparameter, well, I'll explain all that in a minute, is going to be possibly very different values. So you can choose the right hyperparameter to maximize prediction accuracy. So that's, again, staying in a class of models, but choosing the best model using this holdout procedure.
So the output of different, let's say, you have decision trees, it's one class of models. So
Yeah.
What kind of outputs do these models do? Like, what are they?
Oh, well, it depends on the problem, right? So if you're trying to predict the price of a house, that's a real number. If you're trying to predict if it's spam or not spam, that's a binary value, 0 or 1, right? Yes, no. So yeah, that depends on the
So
particular.
input to the model is the features and the labels in the case of supervised learning.
Yeah.
And then what does it spit out? Like
It'll spit out well, once you train the model and then make sure it's not overfitted and all of this, we'll see these notions soon. Then it's ready to predict. What does predict mean? Now data comes in without the labels. There is no human sitting there putting labels anymore. Data comes in without labels, and the algorithm's task is to assign labels. That's called prediction.
Okay, so just assign labels to features.
Assign labels to features that have been projected from the raw data.
Yep.
Yeah.
Okay, so it's going to give you a mapping from features to labels. That's the output.
Yeah, that's right. Yeah.
And so unsupervised will just do it without any training.
Unsupervised, yes, there are no labels.
Okay.
So it's a label-free process. Okay? Okay, good. So I think there's, please watch this later. So all these questions you're asking will be in much more concrete detail on the spam filter with the email example, but 7 minutes, 48 seconds, we will skip. Okay, so now let's get into let me think. I mean, we could do the supervised first or the unsupervised first. What do you guys feel like?
Which is easier to start with.
I don't know. I mean, unsupervised? Supervised? Well, okay. So I think in terms of the concepts you need, this one's actually the minimal actually. It's minimal. I mean, we'll maybe go back around. I think. Is that true? Yeah, I think that's true. Anyway, I forgot a lot of things, so I'm gonna have to learn now. So, all right, so I remember this. So we're gonna do decision trees for handwritten digit recognition, right? So decision trees are actually a lot easier to understand, a lot more intuitive, okay? And original plan was to do linear algebra, but then I sort of decided to do this first, and then we'll do linear regression next week because we need at least 40 minutes of doing distributed linear algebra next week. So this is actually from the Databricks Community Edition that has been added. And I've added the Databricks Community Edition to our shard right here. So you can actually click this and see the original one that was shared in the Community Edition. Did anyone, by the way, get a Community Edition? Did anyone sign up for the waiting list for the Community Edition?
For what?
Okay, that's good.
No, obviously not.
Obviously not. Well, you don't need it now, but you might as well. Then you don't need me or UC or the shard, right? You can just float on your own with the Community Edition.
Is that a free?
Databricks.
Yeah, Databricks Community Edition, sorry. So here's decision trees for handwritten digit recognition. Okay. Now, what are decision trees? What are hyperparameters? And what is it really going on with machine learning algorithms that use decision trees? So these are sort of minimal core concepts we need. The particular data set we'll play with is actually MNIST data set from the SVM lib package. And it's a whole bunch of handwritten digits. And the algorithm basically takes these pixel images with gray level coding, and then it's supposed to learn from the label data, because the label data will have, yes, this is 8, this is 4, whatever. It has to learn from that, and then we're going to basically have some of the data which we pretend we actually don't see the label, and then we'll find out how well it predicts on it. Right? So that's essentially what we're going to do. So it's all the steps that we talked about. Okay. And so our goal is basically to recognize digits, and then we'll have some sort of takeaways from here. So let's first build intuition for learning with decision trees from this wonderful thing I found out. This is the link I sent in the meetup. I'm sorry, I cannot send emails to everyone because it takes me about 8 minutes to literally manually copy through seds and greps and put in the BCC field of the email. So just sign up for the meetup and see your feeds that way. Right, so this is a visual introduction to machine learning, and this thing won some, were nominated for some art awards. It's actually an interesting, it's an undergrad, maybe you're a grad student at Stanford, and then a data artist from New York City, so it's a nice project. Okay, so in machine learning, computers apply statistical learning techniques to automatically identify patterns in the data. These techniques can be used to make highly accurate predictions. So we're going to keep scrolling. I can't embed this. I spent some time trying to embed this in place, but I think it's some kind of an interactive D3 thing. So as you scroll down, the image actually slowly just becomes clear. And I predict in 5 years when my daughters are taking courses, they will start probably saying like, the images are popping before I started reading that part. So this is quite nice, I think. It's very, very beautiful. Notes. Okay, so we're going to basically use this data set about homes. We will create a machine learning model to distinguish homes in New York City from homes in San Francisco. So here's some intuition. Let's say you had to determine whether a home is in San Francisco, which is green, or New York, which is in blue. In machine learning terms, this is, we saw as the classification task, because our goal is it's SF or NY. So since San Francisco is relatively hilly, we can look at the elevation. That's what's shown here. So all these green bars, each one is basically a home in San Francisco, or a density of the number of homes at that elevation, basically. And this is for New York. And those of you who've been to both cities or can imagine, this is quite hilly. So it's a nice feature to try to split on. Okay, so now based on the home elevation data, to the right, you can argue that above 240 feet, because if you see here, everything above this, it's only San Francisco. So, well, that's a good point to split maybe, right? So now let's add some nuance. So we can add another dimension, which allows for say the per square foot cost. So now what we're basically doing is the data suggests, so if you look at it, we have on x-axis the per square feet price of a home, and the elevation is still on the y-axis. So now you can start seeing that there are more patterns now. If you sort of split here and then split on this side, you get all these low elevation, high cost, probably Manhattan homes, right? So that's basically what this is trying to say. So you're trying to, do a partitioning of the feature space to get the blue dots and the green dots in separate cells. That's basically decision trees. And so we can draw these boundaries now, right? And so if a new home comes and it falls in this green cell, it'll be predicted to be that from San Francisco, and if it falls in this cell, it'll be New York City.
What if you couldn't split?
Couldn't split?
Well, look at this box.
Yeah.
They all mixed. It's like, what if you cannot split it further?
Well, I haven't told you anything, right? This is kind of like talking to like babies. Maybe it's two. Maybe we can do the maths quickly. I mean, I haven't told you how I'm going to split. I haven't told you where I decide to split and what dimension I decide to split. All those things are sort of coming in a bit.
Okay.
So you've got to wait a bit. So anyway, maybe is this too boring for people? Has anyone looked at this already? Okay, all right. So anyway, identifying boundaries is important, and so we can look at now we're going to look at just more features. So this is the pairwise scatter plots, remember? So now this data set actually has 7 different dimensions: elevation, year built, number of bathrooms, number of bedrooms, price, square feet, and square feet, price per square feet, and so on. So now the idea is, how do we use all these 7 dimensions, which is our sort of fixed feature space, to try and do this classification task? So the way you do this is essentially, formalize this intuition, is what's called a decision tree. It's also called classification and regression trees. That's the technical terms for it. Okay, so decision trees basically look at one variable at a time and are very, very accessible, so a very popular machine learning technique. So now the question that Andrea asked, well, maybe is finding better boundaries. How do we let's go back and say, why did we choose 240 feet elevation boundary? Right? And to do this, basically what we can do is look at the histogram of the houses in the New York data and the San Francisco data according to elevation. So this says that there's a lot of New York's data that's in the low elevation region, right? And there's sort of a smattering of these San Francisco homes in higher elevation. Okay, so this is officially called a fork. So a decision tree uses if-then statements to define patterns in data. So for example, if a home's elevation is above some number, then the home is probably in San Francisco. That's exactly what we did. So in machine learning, these statements are called forks because they're essentially if-then statements. They're just forking and partitioning the space according to some Boolean conditions. And so here are the 2 branches. And then what we can do is ask, what if this is my split point? Right? I think that's the official terminology. If I've chosen to fork on or split on elevation dimension, the feature elevation, and my split point is 242.8 feet, which is right here, then I can ask, if I look at the left of that split, what is the fraction of homes in New York and in San Francisco? So it's 111 in New York and 92 in San Francisco. And then if I look at the right of that split, I basically have all of San Francisco and 0 New York. Right? So that's kind of the formalizing this intuition. So a split point is the decision tree's version of a boundary. So what are the trade-offs? So picking a split point has trade-offs, right? So our initial split was right there. So if I move the split to the left all the way to 0, then, this is like looking at all of the data, right? So it's just 111 homes. Everything is above 0 elevation, so it's kind of boring. Okay.
But doesn't mean 56% is correct.
Well, okay, so this means, this is kind of the naive, I don't know what it's called, naive classifier or whatever. So basically you can just put all the data together, and if a new data comes in, then it will get predicted to be New York with 111 divided by 111 plus 139, which I believe is 56. Is it?
Right, I understand.
So anyway, I don't want to get too bogged with false negatives and false positives and so on. But basically what we want is the notion of a best split is at the best split, because you have to decide which is the best split, the results of each branch should be as pure or homogeneous as possible. So we want to find a point where the number of green relative to blue is as homogeneous as possible. And if we can somehow formalize this notion of purity, then we have a heuristic that sort of formalize our heuristic, basically. Okay, so this is, you can look it up if you really want to. So in fact, links later, these are two common notions of purity, Gini index and cross entropy. In fact, Kurosh defined cross entropy last week using some very nice information theoretic rules from Shannon, okay, in the machine learning course. So now we want to kind of recurse and start splitting in different features. We have an idea of an optimal split that sort of preserves purity in some sense, and then we want to now recurse across different dimensions. Right? So how do we choose the best dimension to split? Okay, so that's again a problem we need to address, and we can use the same idea here again. We can use the same notion of purity. So we look at every possible feature or dimension, and then find out the optimal split in that dimension, and then choose and be very greedy. This is a greedy algorithm. Be very greedy and say, I will choose the dimension which for the best split gives me the maximal purity. And this is a so-called NP-hard problem to solve it exactly. So this is basically the full algorithm. Okay. So anyway, I think I'll kind of slightly speed up. So this is basically growing the tree. So you can sort of see, I split at the elevation that gives me the best bang for the buck, basically highest purity. And then I split on price per square feet. And then for things that are low elevation, and then for things that are high elevation, I split by price at this optimal point. And I just grow the tree like that, right? Then I sort of look at it and year built and price per square feet and so on. So if I keep going like this, my accuracy keeps increasing, of course. And of course, if I go all the way down and allow as many leaves as I want, then my accuracy will reach 100%, because eventually every leaf will have only green dots or blue dots, right? That's basically what's going on.
But will it exhaust the number of samples?
Yes, well, not quite, because you see, these balls are telling you the number there. So I think this has more than one.
That's right, but is it representative to have 5 or 6? I guess you need to have more. If you continue to split 5 elements into 5 leaves, you will end up with one representative element.
Yeah, that's correct. I mean, we don't need to even go that far down, but we could, in the craziest data set, we could go all the way down and make sure that every leaf exactly has one thing. But we can even stop as long as everything is perfectly pure, right? That's what this is showing. And of course, this is bad. That's the next slide. The next slide saying this is overfitting the data.
So yeah, I'm trying to understand. It's like K to have a leaf which results in one element from the trained data set. even if it's just one. It could be not represented.
Right now, it's okay, because I've said that I'm allowing it to just descend as much as you want. And the next slide says it's not okay to do that, because we want to avoid overfitting.
Right.
And so there's an animation. So let's say we did this, okay? Everyone's with me? We've done this. There are big balls because there are lots of San Francisco homes that were built after that year and that were of price per square feet bigger than that and bigger than that price and elevation greater and so on, okay? So that's this big ball. So now let's say, okay, a new data comes in, right? Or we pretend to take the data we used for this process, which is called training, and stick it back in there and see where in the tree it falls. Then we can essentially do this. This is making predictions, you see? I'm dropping all these data points again into the same tree, and I'm predicting. So the blue and the green basically go to the left and right. So now my training accuracy is, of course, going to be 100% because I'm just fitting, I'm just taking the same data I used for training to put it back into the thing. This, of course, is a debugging, just debugging this. So
searching through your original data.
Exactly. So if you can ask, where did that come from? This is where I sort of went and liked it to vote for this. It's really nice. So it tells you exactly the path it took, right? So it's quite nice, and of course it does it for everyone, right? And here we go. So it's quite cute. So because we grew the tree until it was 100% accurate, right, on the training data.
It's a representation of the original feature.
Exactly. This tree maps each training data point perfectly, right, to which city it is in. Well, it's good. It's a reality check. So of course, what matters more is how the tree performs on previously unseen data. That's the reason why we will hold out part of the data and not use that, not let the algorithm see it. Sort of hold out, right? So that's what we're going to do next. So now, if we did that, what's going to happen? So now, to test the tree's performance on the new data, we need to apply it to data points that it has never seen before, right? So this is called test data, which essentially means if you have a, say, 100 training point, you may take 80 to do the training, 100 supervised labeled points, and then you take, say, 80 to do the training and maybe 10 or whatever, 20 to do the test. That's basically what's going on here. And now we can see the test accuracy is only 89.7%. And of course, we can again look at where it's all coming from, right? So that's the idea. Okay, so this one's less than ideal. Okay, so this is where I found out. Hover over the dots and see the path it took. Okay. So these errors are due to overfitting, right? So our model has learned to treat every detail in the training data, and so we want to somehow control it. So overfitting is part of a fundamental concept in machine learning that they said they'll explain in the next post, and haven't yet. Probably busy studying for exams or something. All right, so this is a spoiler alert, right? This is called the bias variance trade-off. So this is the recap. Machine learning identifies patterns using statistical learning and computers by unearthing boundaries in the data sets. One method of making predictions is called decision trees, which uses a series of if-then statements. And then we have some notion and heuristic on a greedy search for purity. And then we try to avoid overfitting by essentially not letting the decision tree see all of the data. So let's go back, okay, and say, the depth to which the maximum depth I'm allowing in the tree is a fundamental parameter that controls how much I can overfit the data. Do you agree? If I allow like infinite depth as much as you want, then I can just keep chopping away and every leaf will have exactly one data, which is pointless. But I can say, oh, maybe I'll allow the maximum depth. So the maximum depth here is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, right?
That's the number of features.
Oh, the number of splits. Number of splits, yeah. So the maximal depth is basically a parameter I use to control what's called the complexity of the model. Then what I can do is for maximum depth 9, for my holdout data, my test accuracy is basically 89.7%, okay? But if I had a maximum depth of only 7, right? And then I want to know how much is my test accuracy, basically. So I can kind of So now things get more messy because I still want to do the test in the end when I've fitted my model. So now I have to partition the data into 3 blocks, right? I have training data, and I have something called validation data, and then I have something called test data. So it's called validation data because we're doing what's called model validation, right? Selecting the best model from a parametric family. So here the parametric family is just encoded by maximal depth. So maximal depth can be 0, which is that silly example, all the data, or 1, 2, 3, 4, let's say up to 9 here, or whatever, or 15 or whatever. And then, so for each maximal depth, what I'm going to now do is use my training data, which could be say 60% or 70%, and I may use the 10%, or say 60, 20, 20. So I'll use the 20% to do validation, which means for each value of the maximal depth, I will go dump the validation data and see what is the accuracy, what is the prediction accuracy, right? So that gives me a mechanism to choose the best maximal depth. Okay, is everyone with me? And once I've done that, I keep my remaining 20%, the other held out bit that the algorithm has not seen during the training phase or during the validation phase. Now I take that and then I do this process and get the test accuracy. So this is basically machine learning. I mean, that's the idea. And in fact, these books on combinatorial methods and density estimation, this is all the L1 school. It's basically, it's all about the details, the combinatorial details of how these sets are being partitioned. And the combinatorial details matter because the rate at which you can learn, this is called the asymptotic learning rate, depends on the complexity of the sets you're allowing in your algorithm. So, so if you make things arbitrarily complex, your what's called generalizability becomes very, very low. It's like overfitting. So that's sort of, for the more mathy people, that's sort of, okay. How much time did this take? Wow, okay. Was that useful?
Yes.
That's the basic idea, right? Everything basically revolves around that kind of tripartite setup. Algorithms may change, but so here's a nice little wiki thing. I sort of strongly recommend you to sort of go through this a little bit. This is where those notions of impurity and purity are formalized. If you want to get into this, I think let's sort of stay at a pretty abstract level and sort of focus on applications for a bit. But then we can drop into this if you have questions. Okay, so now let's go into loading this MNIST training and test data sets. Okay, so here we're mostly just doing training and tests. So this is your typical example. So it's basically each image is a vector of pixels representing the image of handwritten digits in gray level. So, okay, and so the first thing we do, okay, we attach to a cluster. I'm going to import MLlib utilities. So there's the machine learning programming guide. So we need this load lib SVM file, okay, which is going to be in MLlib utilities that we imported. And this is essentially going to load this particular file that's formatted from this library. So we don't have to worry about the details. So if you use this lib SVM files, then you can just use this loader. And that's a really good resource for machine learning. Now what we've done is created an RDD called training RDD, right? With this MNS digits train.txt data, which is in our distributed Databricks file system. So then we define another RDD called test RDD, right? Which is basically the test.txt data. And then next, yeah.
Just one more question. Is it possible to have a look of the original data? What does the original data look like in the system?
Sure, but not right now though, because you have to go back to week 1 and look at the the head, and there's the instruction on how to get the first several bytes of the file. That's one of the first things we did. You can do the same and find the number of bytes. And yeah, I don't want to go in there now, but we'll start immediately seeing it in data frames because. Okay, so training basically is training. So now I made my training RDD, so I'm going to use the .to_df method to convert that to a data frame. Remember, we want to just leave the RDD land as soon as possible because we're not experts. So that's exactly what we're doing. We just We just make this value called training, and then this value called test, which is again just the test RDD turned into a data frame. Okay. So now let me cache it because we're going to reuse this data. So let's use RAM and cache it, distributed RAM and cache it. So just stop cache does that. So that's basically Control Enter should work. Okay. Oh, did I not do something? Oh, yeah, so it's working, right? So you can, I think Siva is going to go and get into details of like what's really going on under the hood at some point. Okay, so you can look at the jobs as they're happening and blah, blah, blah. So we have 60,000 training images and 10,000 test images that have been loaded. And we have basically done our tasks. So now training is a data frame that's cached and test is a data frame that's cached in memory. Okay, so this is, so we could have easily done this because we're on Spark 1.6. So now let's use this display command and see this. So this should answer your question, Shrivan. So, okay, we're not seeing the raw bytes because I don't really know what format that file lives in. But so here's the data frame once it's been loaded. So what you can see is, so here's basically your image. Each image has the true label, which is the label column, which is here. So this is 5. This is how 5 looks in grayscale. So, well, so it's a vector. So this is basically a vector of features which represent pixel intensities. I think pixel intensities, is this 2 to the power of what? This is it 256 is the maximum? I think so. So so it's between 0 and 255 maybe. Right? These are the pixel intensities in grayscale. And so we see label 5, 0 looks like this, 4 looks like that, and okay, that's our raw data.
Does it matter the dimension because there is no point where this point is?
Oh, I'm sure it's all in some global in some globally agreed coordinates, probably like zipped like this. I don't know. They all have to be right, otherwise I can't randomize. Okay, that's a different problem. I didn't check that myself, but I'm assuming that should be the case. Okay, because we're splitting, you'll see we're splitting on dimensions, so they all have to agree on what they believe is dimension 1 and so on, which is basically which pixel.
Yeah, so it matters as long as they're consistent.
Exactly, it should be probably overlay. It's probably just what is that called? Mod indexing of 2D to 1D.
Probably the SVM has a 3 to 1.
Yeah, yeah.
I think the person who made the data set cleaned it up. Yeah, I think he cleaned up the data set and displayed it.
Yeah, sure. Yeah, so I think it's definitely, yeah. So pixel 158 and pixel 160 are the same pixels if you overlay it. Okay. So train a decision tree, right? So here basically is our sort of main thing. What we're going to use now is all these fancy pre-made tools in ML pipelines, right? This is essentially what I hope will be useful for people in the industry. Right? So we're going to use this thing called the string indexer, right? So before training, we want to tell the algorithm that the labels are categories 0 through 9, right? Rather than continuous values, because these are otherwise seen to be interpreted as numbers, right? So for that, what we're going to do is use the so-called string indexer class. So that's essentially, and then we're going to use this in this sort of machine learning pipeline. So pipeline basically is various steps we're going to do to our data frame that we have now. Okay, so and definitely knock yourself out in the ML pipelines user guide. So here's in place embed of it. There's quite a lot. We already know what a data frame is. We will see what a transformer is and an estimator is and a pipeline is in this example. Okay. So we'll sort of do it, and then later on people can go and follow more details. Okay. So now the first thing we're going to do is import the various ML algorithms we will be using. So we're going to import org Apache Spark ML classification and then decision tree classifier and decision tree classification model. These are sort of specific modules we are importing. And then we are also importing ml.feature string indexer, and then the ML pipeline itself. So let me just import all that. So string indexer, so you basically read input column label and annotate them as categorical values, right? Not continuous numbers. So we're going to simply say val indexer is new string indexer, and then the method is dot set input column as label and set output column as index label. So of course, you ask, where is the data frame here? Well, it's not there. It's just that we're just, you know, I don't know what it's called in Scala. Is this a constructor? Or, so we were just, you know, creating an immutable value called indexer, which is essentially a new instance of this class which is going to expect whatever is fed into it later to have the input column as label, and the output column will be called index label. Yeah, okay, so I don't know what's really going on in the code, but it's kind of obvious to understand from the code. So this is basically now the decision tree classifier, that's called DTC. So this is going to learn to predict column index label using the features column, okay? So here's basically my set label column to index label, and it's going to, so I'm, you know, imported this method, which is going to do all the magic for us, and then it's going to set the label column to be the index column that this indexer has done for us. So finally, we have this pipeline. We chain this together, the indexer with the decision tree classifier DTC, and call this our pipeline. Val pipeline is new pipeline dot set stages, and in the set stages, we essentially have an array of different parts of the pipeline. First thing is the indexer, and the second thing is the decision tree classifier. So the pipeline is set. All it needs is the data frame, right? So once you put in the data frame, it's going to just do the steps for you. So this is basically how you fit the model now. So you say,
Right.
Yeah.
Because it's supposed to be that we actually tell our classifier where expected known labels are, but we tell only where the output of the indexes is.
No. We're saying set input column to be label. Remember, label is the name of the data frame we're about to pass into it, because that's its column name is
This is
label.
the indexer, but the indexer does nothing to the classifier. The classifier only looks into the indexed label.
Yes, that's correct. So once I run this,
Together. So what the indexer does is to transform your label into indexed label, which will be something that the decision tree classifier uses.
the decision tree classifier looks at the string version, the string converted version of the column of the original data frame that's called label. So you'll see this, right? So let me just, so now we fit, right? We're putting training, and training is the data frame, right? The training data frame. We put it in. It's going to take a.
Is the indexer going to add a new column to the data frame?
Yes.
Yeah, absolutely. Right. So yeah.
It also has to remove the old label column.
Okay, so I don't, so as far as I've seen in ML pipelines, data frames simply keep adding more columns. Because we told remember we told here that set label column to be index label.
Why doesn't it use the label column as a feature?
Because the label column is actually not a discrete category, because 0, 1, 2, 3, 4, 9 is actually just.
That's why we don't use it for specification. Why don't we use it as a feature?
Because it's not a feature, it's actually a label. So label, remember, this is supervised learning, so you have labels and features.
Yeah, how does this?
Because we specify here, right? We're saying DTC is the new decision tree classifier, where we're setting the label column to be the index label. I mean, this is all compressing a lot, but yeah.
Right, so the index label is not an algorithm.
No, that's right. That's just been added by string indexer, you see. So string indexer takes the label as input column and sets the output column to be index label. So when the data frame comes in, it'll take the label column and add another column called index label. And
In this new data frame,
yeah,
we have a column called label and column called.
index label, absolutely.
So why does, and we're doing training classifier on the index label.
That's correct.
And using what left to the feature.
The entire gray image, the integer vector. That's the image.
Okay, but no.
That's the features.
But why doesn't it look at that and say, well, it's column called label?
It takes the features, from the data frame, it takes the features column and uses that as features. So it's a column. Yeah.
Yeah, I mean, there are only two columns, right? Okay, let's go back. So let's go back, right? So basically there are two columns. One's called label, one's called features. And so there's nothing,
So can you just give an example of, say, for the first row?
Yeah.
What would be the index label?
So it'll be the string 5.
Yeah. So just converting that to a string.
Yeah, exactly. So that's
But it does take into account features.
yeah, features are just features, right? Features are fine. They're just
So just converting it to a string, and the second thing is one set as a string.
yeah, because so basically we begin by training a decision tree using the default settings, right? So before training, we want to tell the algorithm the labels are category 0 to 9, not integers 0, 1, 2, 3, 9, which have a metric implied. Okay, that's the reason. So rather than continuous values, right? That's the we don't want to avoid it. So what we do is string indexer class to do this. The string indexer just turns into a string and end the story. It's a discrete object. And then, so.
So what's the significance of this, of there being a distance between two things? Like, what's the significance?
It's just that you can get at the I mean, let's cause it's kind of getting to, because we have a lot to cover, unfortunately, right? So I'm sorry, but we can get into this later offline, right? This is something you have to descend in. So let me just kind of slightly speed up because okay, so basically I'm not sure if I hit this. Okay, so yeah, I did fit it. So once you've done the fitting, the point is it's quite simple. You just set up a pipeline. Once you understand the syntax, it's just done, right? So it's very, very straightforward. And let's now inspect the learn tree. If you just hit val tree to be the model.stages.last as instance of decision tree classification model, okay? I can't explain all the details of why that's the case. You can descend into it. Then we can display the tree. We can actually see what it's done. It's taking feature, position 350. Oh, so I was wrong. So there's more than 256 elements to this vector. So it's taking feature 350 and splitting it into a less than and greater than 1.26 times 10 to the 2, right? So it's basically doing your divisions right here, right? So it's, of course, exploiting the fact that these features are grayscale values.
No, this is the index in that array.
I think so. I think it's the index in the array.
And the number of features will depend on how dense you put your program.
Yeah, so let's see if we can, I mean, I unfortunately don't.
It's 780.
You see 780, good. Okay, we're all happy. Oh, okay, okay. Okay. All right, so let's see. Okay, so this is kind of nice, right? So this is one of the nice things with display. So not every model is currently displayable like this in data frame, but it's very, very convenient. So especially for data scientists to start playing with it. And so now, yeah. So here's my. This is saying this is 1. This is 4, 9, 7. These are all your digits, the discrete categories, the labels. Okay. So there should be just 0 through 9 in the bottom. Of course, it's very difficult to interpret this. This is kind of like grayscale chopping recursively.
How does it know that it needs to look into the features parameter. We didn't tell it.
Because it's called features.
Right, so it's just some implicit things happening here.
Okay, so so hyperparameter tuning, right? This is kind of important, right? So remember, even in that little picture, we saw the depth, the maximal depth that we allow in the tree is actually a hyperparameter. Is a hyperparameter. So we want to basically find out what is the optimal hyperparameter. So that's the next step. So this kind of tells us the basic state of the art for hyperparameter optimization. And the simplest thing people do is grid searches. Okay, so you set a grid of different maximal depths, and then you will sort of search over this grid. So in 1D, it's just a bunch of numbers. But you can have, is there anyone here that's into? So what is another hyperparameter you can have for decision trees? What else could you have besides maximal depth?
You can choose which value to look more frequently than another.
Actually, if we go to the documentation of this one, they have different hyperparameters.
Yeah.
Like maximum bins is what they have.
Right. Oh, that's for discrete, yeah. For discrete categories. Yeah, that's right. So because for discrete categories, again, the way you split this also, the classical, the standard split will be for a discrete feature, right? You split on whether it is this feature or not. That's your sort of standard split. But you can also split in more complex ways. Okay, so we're going to explore maximal depth here. We're going to train trees at different size. So I'm going to run this because it's going to take a little bit of time because it's basically doing varied max depths model. So I have a loop from 0 until 8. 8 is the maximal depth, 0. And then I'm mapping, right? I'm mapping 0 through 8 sequence into my closure here. And this basically is taking max depth will be 0, 1, 2, 3, and so on. So for each of those, I'm actually doing this full training. So I'm basically doing, take my DTC, set max depth to be, whatever this particular max depth value is in the loop. And then I create my pipeline, which is all ready and set up, and I just do set stages and array indexer to my conversion to string of the label, and then I'm just using my training. So then finally, I'm doing my fitting, and now it would have done all 9 things in parallel. So this is quite nice and quite fast.
So why is it called hyperparameter?
Why are they called hyperparameters? I guess because the model itself can have parameters. So these are the one level up. Yeah, there's a one level up. I think, is that right, Dominic? Yeah, I mean, I think so. It's probably the etymology probably is that, that's my guess. Because often you'll have models where you have to say if it's a Gaussian model, estimating densities of Gaussians, then the mean and the variance will be parameters in the model you have to estimate. And then, so in our case, actually, the parameters are where exactly to split and which dimension to split within that maximal depth, see? So those are already optimized, according to some loss function. Okay, so it's done. The Spark driver has stopped unexpectedly and is restarting. Your notebook will be automatically reattached. So that's sad. So it's attached again. So should I just try again?
Should
Or it worked for some people.
Yeah.
But I don't think the objects are going to be. Yeah. So anyway, maybe we overloaded the cluster. I have no idea. Yeah, I think yeah, it's probably restarting. Yeah, it's probably a load thing, right? Because I haven't calibrated all these things. So if you look at the cluster, it's all running. So I mean that's a lot of work, right? So you basically 10 people are doing nine tree over 54 gigs in. So yeah, so that's I'm not too surprised.
You can wait while you
I mean, I think the basic examples will still make sense because I think everything is. So let's go into this. I don't think we're going to reach there today. It's okay. So decision trees. Let me just show you basically what the end of that loop. Like what we would have done is actually gone here, and we're going to define an evaluation metric now, right? So this is the part where we're going to actually use something called precision, right? This is essentially 1 minus the prediction error. So this is going to be our evaluation metric, and we're going to use this evaluation metric to see how good each maximal depth is, right? And so, that's essentially what this one is doing. So I'm basically saying my evaluator is going to be this sort of multi-class classification evaluator. It's multi-class because it's more than 2. And I'm going to, again, set the metric name to be precision. And essentially that would have given me some evaluator defined. And then for each maximum depth setting, I'm going to make predictions on the test data and compute the accuracy metric, right? So that's essentially what this loop is going to do. So once again, accuracies is going to be just a loop over 0 to 8, and I'm going to be mapping the maximal depth to my model, which is essentially going to be varied max depths model of max depths, right? Which is basically here, right? So I'm going to redo all of this, and then I'm going to do my predictions, right? So to do the predictions, I'm calling this transform method on the test set, and it runs the fitted pipeline basically. So the learn model makes predictions on each test example, and finally I'm going to make this tuple, which is max depth and evaluator.evaluate predictions. So now I'm going to just finally turn that into a data frame and call it max depth and accuracy. All of this should work. And then I'm simply displaying it here. So let's sort of say you can maybe trust me and run this later on. And then the max depth is 0. My accuracy is 0.113. And you can see accuracy is improving with the depth. Okay, so that's essentially right. So now we have to, of course, worry about overfitting. That's the whole reason. So if you keep increasing the depth, we're going to basically, reach 1. So what we want to do is to do some kind of a held out to tune these parameters. So this is the exploring max bins bit. This part is essentially controlling, is simplifying things. So later on, what we will do is make the pipeline a bit longer and actually do the full thing in one go. So we will basically do the hyperparameter checking. We will hold out the data, do the validation, and then finally test the data as well. And this last bit is basically saying, well, let's just make the number of bins to be just 2. So this is actually using the intuition that this is a grayscale image, and why should I use all the gray values? Let's call it black and white, right? So if it's 0, it's white. Otherwise, it's all the other values are black. So I can just turn this into a much lower dimensional problem, right? Because you can see that this light gray in the 4, who cares? We can just call it black, right? So that brings us a huge compression of the feature space, or reduction in the feature space, and then you can essentially run exactly the whole thing we've done before, but now just for this. So we basically are allowing the max depth to be 6, and then because we decided to stick with one particular max depth right here, and then now we're just sort of looping through accuracies, and what we're looping through is a sequence 2, 4, 8, and so on. And max bins basically takes 2, 4, 8, 16, and 32. And then for this value of max bins, we're basically going to learn a tree and do exactly the same process and display the accuracies. And we're finding that it's good enough to just have it black and white. Okay? I mean, that's, again, another hyperparameter, you can think of it as. Right? That's the level of projection you really, or the resolution of the data you really need to do this classification. Okay?
What's the default? What's the default?
I think it must be all of it. Yeah, I believe so. Is that right, Siva, you think?
Right.
Yeah. I mean, you know, it's a lot of code, you know. So
I'm just saying, like, so
I think the default will be everything.
yeah.
Yeah, that's, yeah, because we yeah, I believe so.
That's like also name the data, isn't it?
Yeah, exactly.
So that shouldn't be a hyperparameter of the discrete model.
Yeah, it's what we can call it something else, maybe, I don't know. Yeah, it's just a feature. Yeah, it's a feature.
Transformer.
Yeah, something.
But I mean, so what that classifier is actually doing the bin, right?
Yeah.
Making it into the bin. So max bins is the parameter of the classifier because that's what's putting the thing into the bins.
Yeah.
It does seem to be like a hyperparameter.
Okay, these are, yeah, so I think, yeah, let's, yeah, so yeah. I think yes, language is a different problem. So yes, it's something we can tune our model and improve the prediction accuracy on. That's
It's not like you're doing something to the data.
Yeah.
But the model itself is putting things into bins. And you're just tweaking that to say, don't put it into the
Sure.
bins.
If you say so, yeah, it's totally cool. Yeah, so we can call it the projection operator on the feature extraction layer, or you can call it whichever way you want to put it. Yeah.
Documentation says that the default is 32.
Okay. Okay. Okay.
Okay, so it's going to do that anyway. So it's nice to use, like in the previous one, even if it had lots of like values, it's going to do very good.
Yeah, I guess so, yeah. All right, so I hope this gets you somewhere. Here's essentially, I was going to do this, but it's way more complicated. So what you really want to, this is all sort of homework for you guys, or whatever you can explore. There's something called random forests, which are actually now ensemble methods where you don't have just one tree, you have actually an ensemble of trees, and you actually query every tree in the ensemble and find the average and things like this. So these are much more robust and sophisticated methods and very good properties. I have not written any syntax for this, but you should be able to do this with a little bit of, being a bit stubborn, basically. And the blog posts are quite good. There's gradient boosted trees. So these are things I think, those of you who are taking machine learning, you'll understand them in a fair bit of detail. And, you can come back once you know the concepts and then start coding and playing with it. Okay. Sorry that this cluster crashed. Okay, so the other thing here, let's sort of give you a flavor for this. So maybe we can call this homework. But, the basic idea is now we're going to do unsupervised learning. Okay, so this is the other big branch. Okay, and what I'm going to basically do is do the following 3 steps. This again is from the Databricks guide itself. Okay, so it's slightly augmented. And this is the million songs data set. And what you can do is ETL, extract, transform, load, like we saw before, explore the data, and then we're going to do the modeling. And the modeling we're going to do is what's called k-means algorithm, right? So this is a very, very simple, intuitive, easy to understand algorithm, just like decision trees are. Okay. So in the ETL step, we're basically going to build RDDs and then transform RDDs, use some schema, and explore using data frames, create temp tables and cache tables. So this is from last week's stuff. So it'll be a nice review. During the exploratory phase, we're going to use the same, use schema and do some displays and visually explore the data. And I think we couldn't get the ggplot to work in Scala. So it's that part is still in Python, I think. So, and then finally we'll do the modeling, right? So for this modeling, our goal is to essentially discover structure in this data. There is no labels, so it's unsupervised. So these models are essentially, and remember in Amit's talk, he was pointing out that the unsupervised learning often can be a loop in the feature engineering bit. So even in supervised tasks, you may want to do unsupervised learning on the original raw data to actually find the right features to extract for the supervised task. So that's a standard thing. Okay, and that's the plan. So let's sort of jump into the 1 million songs dataset, ETL. Maybe I should try to.
Right, it's a little bit unclear.
Yeah.
You said that we can use unsupervised learning to find out the right set of features to extract.
Yeah.
But if features are not extracted, how would you do unsupervised learning if there are no features? If they're not extracted?
No, what I mean is, so say you have some data that's in a supervised setting, right? So you have some labels and so on, but there's like thousands of whatever columns, let's say, right? Now, most of those columns may be very meaningless, highly meaningless.
Mm-hmm.
And now the task is how do you extract some meaningful columns or projections of columns into a lower dimension, basically.
So you have got them extracted, just pick most important ones.
Exactly. You can think of as picking the most important ones, or in fact doing something else. So these methods also go by multi-dimensional scaling or dimensionality reduction methods. And k-means is a baby, but it's a Gaussian mixture model based idea where you're trying to find clumps and communities and things like this. So maybe you can find communities and clusters and then use those communities to maybe do a better feature extraction or something. So, okay, so let's see. All these clusters are supposedly running, right? So I'm not really following why I can't. Okay, so I guess I'll just leave it and see what happens. You think? So if something crazy happened. Because it'll be fun to just I'll just go to this one. I hope that's not overloaded. Yeah, well, we'll see what happens. So maybe it'll be nice if you guys try not to click it in the other cluster. We have finite resources, right? There's like maybe 3 or 4 people gave the AWS credits, so can't just make this too big. Okay, so text data, this is so we just look at the file systems. So here's our, songs data set, and we see that there's data 001. It has a header.txt, and then the rest are all parts. So these are parts because of the distributed file system numbering. It's quite a lot, 119 of them, right? The sizes. So now we're basically going to do a collect. Okay, so, and we're just doing a collect on the header, right? Which is just going to tell us this is an array of strings, and there's artist ID is a string, artist attitude is a double, and so on. So this is essentially what is in the content of the text file. Okay, so anyway, if you really want, you can do this. Just to see it a little bit more nicely. Okay. So it's quite a lot of information, right? The duration of the song, end of fade, loudness, song ID, song hotness, time signature, year, and so on. So now let's look at this thing. Let's basically create a val called header, which is basically going to split my line that we saw by the colon character and simply make me tuples of header element 0 and 1, and I'm collecting that. So that's my header. So now let's define a case class called songs. and that'll be used to represent each row of the data in the files, right? And that's just right here. So case class is a very, very nice way to read in pre-structured data, okay? And so every row that comes in into the RDD will essentially see this case class, and this is a natural way to turn it into a data frame. Okay, so defining a case class called song. And then now we turn we first create an RDD called data RDD, and you see I put a star operator here, so it's going to read all the files that start with part 000 to the 119 of them. So now that's my RDD, the resilient distributed data set. I'm just taking 3 just to make sure that everything is okay, at least top level. So I'm seeing various, not a number, row 16, and so on. So each line of the data consists of multiple fields separated by tabs. I noticed that. So I need to have some sort of tab delimited splitting, right? So we've already created a case class. So now let's just use that. And we will just create a function that takes each line as input and returns the case class as output. And that's basically all we have to do. This function is going to take a string called line as input, called the function's name is parseLine. And it's going to return the case class song. And inside, I'm basically splitting the line that's passed in by tab. And then I'm going to basically create, so I'm calling that tokens. And then I'm just creating a case class song of tokens of 0 all the way up to 19. Okay. And I'm doing all my conversions here. So it's dangerous, but this is very clean data. So it's okay to do it. Okay. So now we're going to create a parse RDD. So this is essentially going to map the parseLine function, this is a user-defined function, into my original RDD of lines from the text file. So now I'm going to convert an RDD of case class to a data frame. All I have to do is 2df. So now I have my data frame, which is my 1 million songs. Okay. Now I'm going to register this as a temp table. Okay, so called songs table. So we also saw that last week. And now, right. Next command will throw a parsing error. So what we're basically, so if you look at the exceptions, floating decimal. So the error means that we're trying to convert a missing value to a double. So here's an updated version of the parseLine function to deal with the missing values. So I don't know, Shin is here or no, Shin isn't here. Okay. So this is a question she asked, I think, last week. So how are we going to do this? We're basically going to now expand on the parseLine function. We're going to define another function called toDouble. And it's going to first do a try catch. This is sort of computer science. Do you do this in 121? Try catches in COSC 121? Towards the end of it, yeah. So that's the prerequisite here. So yeah, so you basically try to take the value and do a toDouble and then catch with this exception, and essentially, and then this is the same for toInt. So when we convert toInt, remember we kind of did this all like dangerously here, right? So the data isn't really really clean. Or did we do that right here? toDouble, toInt. So now we're just guarding for some exceptions, and then now we do the same thing, and so this is a bit more robust. So now let's try caching the table. Okay. So after we cache the table, we can just query using our usual SQL syntax with select star, which is every column from the table. And then we just limited the top 10 entries. Okay. So that's, and we're just seeing artist name is 16 and whatever, duration of the song and so on. Okay. So So that's essentially exploring the data. This is just a recap of last week's SQL and data frames. So now let me just get into this. So this is the 1 million songs k-means example. We're going to explore the data now. So we already saw this. And oh no. What's going
Maybe
on?
we should just put the rule that nobody else works except you.
Well, actually, I'm not sure, right? Because there's like 25 notebooks there. So, sorry about that. So, let's see. Should I maybe detach and reattach? The table will still be there, right? So, yeah, I'm not sure what's. I mean, we're slightly under-resourced, maybe. So let's see, there we go. Now, let me just print the schema, right? So should be able to see all of this. So the artist ID is a string, which is nullable, and latitude, longitudes are doubles, and so on. So now I select count star from the song table, so I should see that this is 28,246. Okay, and of course, this is just the data frame API version of the same thing. So now what I'm basically looking at is I'm selecting duration and year from the songs table. And I've used the aggregation to set the average in the plot option. So I'm actually seeing the average of the duration of the songs by year. That's what this plot is. So I don't know, is this World War II or something? I don't know why sort of average duration of the song went down. Okay, and then I think this must be, I don't know, maybe the hippie face or something. I don't know. People are like, have more time to listen. I'm just bullshitting now. So anyway, you're supposed to do this, right? This is a very important aspect of exploring the data and so on. Okay, so now here are some exercises, right? So why do you think average song duration increases dramatically in the 70s? And we can try to add error bars with standard deviation around each average point in the plot. How did average loudness change over time? How did the tempo change over time? These are things you can actually do and explore. I strongly recommend you do it. It'll sort of cement ideas from last week. Okay. And then this bit still works, right? So we didn't have enough time to figure out how to do this in Scala yet. I'll try to fix this. So now we're just sort of dropping into Python land to use ggplot. So let's use ggplot from Python. So from ggplot import everything, and I'm basically using Python PySpark syntax now, just because ggplot is nice in Python. Okay, and I'm able to see year and duration with these things. So this is actually from the original Databricks guide, because it was originally in Python. We just tried to put it in Scala. Okay, so you can try more fancy exercises. If anyone figures out how to do this properly in Scala in the next couple of days, let me know, so I won't work on it.
What was the line split in black? What was the
That's, I think, the mean, and then there's some standard deviation, assuming some model. It doesn't, it's yeah. I mean, it's just a ggplot thing. Won't take it too seriously. Now, here's our sort of real thing. We spent a bit of time on other stuff. So I'll try to go through this. So we're going to start modeling now. So we want to use the k-means algorithm. So the k-means algorithm, basically, to do this, what we need is something called a vector assembler, because the k-means algorithm essentially tries to see data as a bunch of points in a Euclidean space. So it should be continuous values. And then it tries to essentially find clusters there. Right? So we are going to just use duration, tempo, and loudness. These are not sort of continuous real values. So it will be like we should be able to observe this in 3 dimensions, right? Duration, tempo, loudness. So every song will be a dot in the 3-dimensional Euclidean space. And what we're interested in is finding clusters without any supervision, right? That's basically. So to do that, what we need is something called a vector assembler, because the input to the k-means algorithm expects vectors. So then we use this vector assembler in the ML feature module, and so the training data basically is an instance of a new vector assembler, and we do dot set inputs. Input columns to be the array. See, these are the column names in the original data frame: duration, tempo, loudness. And we set the output column to be features, right? So we just call it that. And then we do the transform, where we transform the table. And the table that we're transforming is a songs table, which is basically the data frame is table. Right? So let's try that. Oh, great. Why this is happening? Let's try one more time. So maybe I'll go to, I should be here. So let's see. That works. Okay, so yes. So what I've done is created a training data, which is org Apache Spark SQL data frame. So I've just created a data frame. And if you look at the data frame, it's almost like the original data frame, except now we have this last extra entry called features, right? That's a vector, so it's just adding extra column now. And then that's basically what's explained here. And then if I just take the first 3 entries of this training data frame, I notice that you see the first row is here, 213.7, 125.88, 12 point, blah, blah. These are the three things we wanted, okay? And the next entry also has these 3 numbers and so on. So what's a transformer? A transformer is basically an abstraction that includes feature transformers and learn models. Right? So technically a transformer implements a method transform. That's what we've done here. Right? We have transform. A feature transform is a very nice way to take a data frame, read a column, but it can be text or whatever, and then we map it to a new column, and this we're going to call feature vectors here. And then output a new data frame with the map column appended. So this is the idea. So now a learning model might take a data frame, read the column containing features, predict the label, and for each feature vector, and then output a new data frame with predicted labels appended as a column. So that's essentially what we're going to think of the learning model is doing. Now what's an estimator? Estimator is actually close to what the statistical notion of an estimator is. An estimator abstracts the concept of a learning algorithm or any algorithm that fits or trains on the data. Okay? So technically an estimator implements a method called fit, which accepts a data frame as input and produces a model, which is a transformer. Okay? So for example, for logistic regression, which we haven't seen yet, the logistic regression is an estimator, and calling the fit trains a logistic regression model, which is a model and hence a transformer. So we'll kind of see this many times over the next several weeks for different machine learning algorithms. So you will get the idea, because all these abstractions flow nicely generally through all the machine learning algorithms we'll see. Okay, so now I'm basically displaying the training data and selecting the duration, tempo, loudness, and just the features, the last column and these 3 columns, and just making sure that this is actually correct. 213 is 213 and 7 and so on. So this is, okay, so I'm not sure what happened there. Right. Oh, right. All right, so this might be my own bug. I think so. Oh, let's just delete it. So demonstration of the standard algorithm, right? What's really showing is the k-means in animation very, very quickly. So in step 1, what I'm seeing is a whole bunch of these gray dots are actually the data points. And initially, I'm going to say k is the number of clusters. I'm saying it is 3. Okay, so the 3 clusters. I'm initially going to randomly throw 3 points on this little grid of these gray points. So red is 1, green is 1, and blue is the other. So I just randomly throw these points. And then the K clusters are created by associating every observation with the nearest mean. So I basically take this gray dot and associate it with green. And so essentially that gives me my, my next step, basically, right? So this point goes to this red dot because that's the nearest cluster center, and all these blue, these guys become blue, right? So the partitions here are actually the Voronoi diagrams. You know what that is, and chase that here. That are generated by the means. So for Voronoi diagrams, you have like some notion of centroids, which is these circles. Okay, so the centroid of each of the K clusters becomes the new mean. So this is the next step. So what I'm doing now is basically asking, you know, I'm assigning the new centroids because I take all the green points, find their mean in each coordinate. That basically is my my new green. See, and then is my new red, because in this case there's only one point. This point moves there, this is the mean. And so now I have my new centers. And then what I do is I go back and reassign all the points back to the new centers. So that's the idea of k-means, right? And I keep iterating this until I reach a local optimum. Okay. So, so local convergence reach. So the assignment, step 2 is called assignment, and it's also referred to as the expectation step. And the update step is step 3. It's called the maximization step. Those of you who know about expectation maximization algorithms, this is actually nothing but a specific example of what's called a generalized maximum expectation maximization algorithm, where the underlying probability model is actually a Gaussian distribution, a mixture of Gaussian. Gaussian is just bell-shaped curves in 2D here. And so you have a mixture of Gaussian distributions. There are 3 Gaussian distributions whose means are evolving according to the algorithm. And the variance is spherically symmetric, which means there's no ellipsoidal assumptions on the, so it's all variance 1, basically. That's essentially the probability model under the hood, if you want to interpret it like that. Okay, so now there are big caveats. So k-means is a heuristic algorithm. There is no guarantee that it will converge to the global optima. In fact, even for 2 dimensions, there are very beautiful, simple examples that will show that the algorithm will never converge. So it's, you know, but of course, it's still quite useful in most, you know, real world configurations of the data. Okay, so you can sort of see more of these details. And in fact, this is a much more formal pseudocode definition of this. And I just took all of this from Wikipedia, basically, upstairs there. Okay, so here's a caution, right? So this is a famous iris flower data set. So if you run the k-means cluster with some initial conditions, and it'll say that this is cluster 1, the blue is cluster 2, and the green is cluster 3, because you say k is 3. And then here's the actual species distribution. You know, this is Linnaeus' Latin taxonomy, right? So that's what's reality. This is kind of what the k-means algorithm predicts. So yeah, so it's, you know, it could be completely wrong. Okay. So note also that k-means is non-deterministic, so results can vary, right? So that means it's not going to give you the same answer every time. So cluster means are visualized in this example using the larger ones. And so for different initial conditions, you may come up with different clusters. Okay. So let's see. So we can almost finish this. So let's have a pass through this. And now what we're going to do is try to fit this. So I'm going to say model is new k-means set k, the number of clusters to, and fit the training data. Let's see if all of that nicely works out. So we're going to see if we can categorize it into just 2 clusters. Right, this is our three features we chose.
Is there any influence on where we place random nodes?
Yeah, so I think there are different initial conditions. I think the one I showed you is called some guy's name here. So there's all you know, various choices, the 4G, whatever. There's various choices for the initialization group. I believe I think the default is a random initialization. I don't know. So let's see. That seemed to have worked. So now let me just place the cursor and just show you there's quite a lot of these things you can do. right? So you have to dive into the programming guide to really, you can ask what the cluster centers are, for example. That's what we'll do next. So get cluster centers. So this says these are the cluster centers. You see, 209. So this is the three, the point in 3 dimension for one cluster center, and these are the other 3 points in 3 dimension for the other cluster center. So that's what we've done. And then this is to get predictions in the last column. So it's just that's simple. We just do model.transform, and now we can find out what the schema is. So, okay, so this one is the original training data where we have all these features turned into a vector for the input to the algorithm. And then model transformed is essentially the same, except now we have predictions as well. So these are the
Prediction to what does it mean?
So the new column prediction is basically, it contains the predicted output in the sense that which cluster the data point belongs to.
There will be a number from 1 to 3.
Yeah.
Or it's still the distance.
There are only 2 clusters, right?
You have 2 clusters.
Yeah.
Okay.
Yeah, K was 2. Okay, so here is basically, I'm now just going to choose just those columns, the duration, tempo, loudness, and prediction. And now I'm just going to show this to you. So I'm only sampling a fraction of the data. So duration, tempo, and loudness. Prediction is, cluster 1, cluster 0. So somehow we're we're sort of partitioning the 3 features into the 2 clusters. Okay? And this is just a scatter plot matrix quickly for the 3 variables, so loudness, tempo, and duration. And then this is basically symmetric, right? So we can just look at this. So now what you're now seeing is that, so the details are here, how to get the bi-colored plot. So here we're basically seeing that the splits right here into 1 and 0. And so a good, data analyst will say this is kind of bad. There's a big problem here. So we have to actually do some transformation of the data. Right? So if you look at, you take the transformed and sample it. Actually, I'm sampling all of it. And then I select duration and prediction. I'm actually seeing that there is going to be zeros are split right here and ones are split. So what I can actually do instead is to do a log duration, right? Where I'm doing a log transformation. This is a very standard thing one does. And if you do log duration instead of duration, because I'm basically doing my data frame tricks here, right? I'm taking log of duration and then calling that log duration. And then I'm, again, doing my training data too, which is a vector assembler that takes log duration, tempo, and loudness instead of duration, tempo, and loudness. And then it's setting the output column to features. Now I have nicely my output column.
Russ,
Yeah.
could you please come back and repeat why
So
you
this is
guessed
the reason.
that duration was cause of a problem? What was the problem?
So basically duration is kind of, so when you take log of duration, basically the things that are really on the right extreme end, I think it may be the 1970s, I don't know what it is, but the data was just too spread out. So when I take the log transform, log is a monotone increasing transformation. So things that are far away are kind of brought more in. So
I understand. I don't understand how you noticed that and why you noticed particular duration but not tempo loudness.
Because it was only split along. Okay, so that's so it's only split along. You see, I look here and say, oh wow, everything is just split on duration. You see, the blue and the orange. So it was not like just forget about these bottom ones, right? Just focus on the top. So I was like, well, that's kind of bogus because it's like, so that's basically right. So now it's a little bit better, right?
Right, I see now.
Okay, so that's so there's a very, very elementary example of feature engineering. Sorry, I went over by 3 minutes, but okay. So I hope that was a, reasonable tour and please go back to these examples again. And
It's very good.
what was good?
Very good.
Oh,